So folks, we're continuing our discussion of rational inequalities. Again, our goal is to be able to solve inequalities of this form, inequalities like these down here, and this one here. Before we do that, I'd like to do a quick brief review of solving linear inequalities and comparing them with solving linear equations. So the key word here is linear, and this is not what we're studying today. Today we're studying rational inequalities, and so I want to draw a distinction between the two. If I go to solve a linear inequality, we solve sort of the mechanics, the algebra of trying to figure out what values of x make that true are very similar to our steps of solving an equation, although they are not the same. So 6 minus 2x is equal to 18. We call this a linear equation. It's an equation because of the equal sign. And if we try to isolate x, we end up with minus 2x is equal to 12, or x is equal to minus 6. Okay, we get the sole solution. We get the sole solution to this, x is equal to minus 6. Okay. Over here, we're going to find all of the values for x which make this true. And if you were to just guess and test, for example, if you were to plug in 5 in for x into this equation, you would get a true statement. Notice you'd have 6 minus 10 is negative 4, and sure enough, negative 4 is less than 18. So negative 4 is less than 18. That checks. Or if you were to plug in, let's say you were to plug in x is equal to, say, negative 4 into this equation, you would end up with 6 minus 8, or you'd end up with 14 is less than 18. I said 6 minus 8, I should have said 6 minus a minus 8. And you'd end up with 14 is less than 18. But if you were to check, say, x equals minus 9, you'd end up with 6 minus a minus 18, which is 24. 24 is less than 18. So you can see that sometimes we got true statements, sometimes we got false statements for different values of x. Well, it turns out we can solve this linear inequality, so it's still linear. We're not squaring x, we're not dividing by x. We don't have a rational inequality here. We can solve this similarly to how we solve our linear equations, with one notable exception. So if we go to isolate the variable x, we would end up with, again, negative 2x in this case is less than 12. And then remember the rule that when we solve for x, whenever we divide or multiply both sides of an inequality by a negative number, we reverse the direction of that inequality, and we end up with x is greater than negative 6. So as long as x is larger than negative 6, this statement will hold. And notice that checks with these two values that we looked at, and that explains why this value failed. But now when we go to give our solution, first of all, we're talking about all of the numbers on the number line. Where's 0 on the number line? It's there. Where's negative 6? It's right there. And we're talking about all the values that are to the right of negative 6 on the number line. So we're talking about all of these values right here. And so we could give our solution to this in the interval notation as negative 6 comma infinity. That describes that segment of the real number line where any value we pick from inside this interval gives us a true statement. If we pick a value such as negative 9 here that's outside of that interval, we get a false statement. So that was solving linear inequalities. Okay. So here's a comment. Students often note that solving linear inequalities seems similar to solving linear equations, and I'll give it to you. That seems true to me. However, we're now getting ready to work with solving nonlinear inequalities, and this is where you have to be super careful. So warning, solving a nonlinear or rational inequality is very different from solving a nonlinear or rational equation. So although these two problems seem kind of similar, solving nonlinear or rational inequalities is completely different. Our process is completely different from how we solved nonlinear equations like quadratic equations or rational equations like the one that we did on the previous page here. Okay. So here I've got a sequence of steps, and we'll take a look at it here. This is about as challenging as these problems can get, the example that I've given you here. And let's go ahead and give it a shot. So if we want to solve a nonlinear inequality, the first thing we do is we set one side of the inequality to 0. we find all the essential numbers. Okay, I'm calling these essential numbers here. Those are the roots to the corresponding equation or values where the inequality is undefined. We then build a number line and we place the essential numbers on the number line. We then pick test points, evaluate each test point, and then we can solve the inequality. Folks, these are the steps. I don't expect these steps to make a whole lot of sense just now, but let's go ahead and practice them in this example here. Okay? So as I look at the first step, notice that we've got a nonlinear inequality, or another way to say that, we've got a rational inequality. It's rational because we've got rational functions on either side, or at least one rational function somewhere in this expression. And it's an inequality because in this case we have a less than or equal to. Okay. So the first thing we want to do is we want to set one side of the inequality to 0. So I think what I'd like to do is let's go ahead and subtract that expression over to the other side. So I subtracted this expression over to the other side. So notice I've now accomplished the goal of setting one side of the inequality to 0. The next thing we want to do is we want to find all essential numbers. So anything that would make the expression on the left-hand side equal to 0, that's what I mean by a root, or anywhere where the inequality is undefined. Unfortunately, most of us cannot look at an expression like this and see the zeros of it, what numbers for x would make it 0, and sometimes we might miss where this is undefined or not. The key here is usually what you'll do here, you'll make this into a single fraction. Okay. So let's go ahead and do that. I'm going to make this into a single fraction, and here I do not have that shortcut that we were talking about on the previous page, so I have to multiply by missing factors in the common denominator. So again, in this case, the LCD, I didn't write it out, let me write it out now. The LCD here is x times x minus 2, and this first rational expression is missing the x minus 2 from the LCD, so I've multiplied by the x minus 2 over itself, a convenient one there. This second term here, the second fraction, 1 over x minus 2, is missing the factor of x from the LCD, so I multiplied by x over x. Okay. And now I'm ready to continue. So this gives me 3 times the quantity x minus 2, all over the LCD of x times x minus 2, minus just 1 times x, all over x minus 2 times x. Let me write it in the same order, x times x minus 2, and we need this to be less than or equal to 0. So now I can write this as a single fraction, and that's been my goal all along. This would give me 3x minus 6 minus 1x, all over the LCD. It's less than or equal to 0. Okay. And now as I finish, we end up with just 2x minus 6 all over x times x minus 2 needs to be less than or equal to 0. Okay. Now I'm ready to go answer the second step. Our goal here is to find what I'm calling the essential numbers. This is anywhere where the inequality is 0 or undefined. So let's just notice that the inequality is undefined if what? It's undefined if x is equal to 0, because that would give me a factor of 0 in the denominator, or if x is equal to positive 2. Notice that the inequality is 0 if what? Well, when is a fraction equal to 0? A fraction is equal to 0 if its numerator is equal to 0. So if I set the numerator of that fraction equal to 0, I end up with 2x is equal to 6, or x is equal to 3. So at this point, I found what I'm calling the essential numbers. These essential numbers will be 0, 2, and 3. I have to be careful, though, because some of these essential numbers are up here because x was undefined at those locations, and some of these essential numbers were up here because x was 0 at this location. So I got to keep this distinction there. So I'm now going to build a number line, and on that number line, I'm going to put all of those essential numbers, 0, 2, and 3. It's important, though, and I think this says this here, it's important here to make sure to label each essential number as either a 0 or a domain exclusion. So notice that 0 was up here, not because it made this fraction 0, but because it made the fraction undefined. So I'm going to write UND, that's where it made the fraction undefined. Similarly, 2 is up here because it made the fraction undefined. But 3 is on this number line because it's where it made the expression 0. And that's important for checking my answers here, for giving the final answer to this inequality at the end. So I've now done step C. I built a number line, placing all essential numbers on that number line, and I've picked my test points. Okay. So now let's go ahead and evaluate each test point and check the sign of the result. So I need to pick test points inside this. So look what I've done here. On this number line, I've labeled my 3 essential numbers. That's created 1, 2, 3, 4 regions. So I'm going to take a test point from each one of these regions. Let's take, say, -1 and 1, and say 2.5 and 4, and I'm going to plug each of these test points into the single fraction that I've built over here on the left-hand side. And what I'm going to do is I'm just going to decide the sign, the SIGN, of this fraction when I plug in the test point. So when I take -1 and I plug it into the numerator of this expression, notice I get a negative number. So if I take 2 times -1 minus 6, that's negative. And if I take -1, that's negative, and I multiply it to -1 minus 2, this is a negative times a negative, that's a positive. And what's a negative divided by a positive? That is a negative expression, so I'm going to put a big minus sign right here. I'll do the same thing with the value 1. Notice if I do the same thing with the value 1, the numerator remains negative. If I plug in 1 for x, the numerator would be negative. And the denominator would be a positive times a negative, so the denominator would be negative. And the quotient of a negative divided by a negative, that would be a positive expression there. Does everyone see what I'm doing? I'm taking each test point and I'm plugging it into the original single fraction over here, and I'm just looking at what the sign is. If I were to take 2.5 and plug it into this expression, 2.5 times 2 is 5 minus 6, so my numerator is still negative. That's negative. But now look at my denominator. If I take 2.5 times the quantity 2.5 minus 2, this is positive. And so we're again negative inside this region here. And lastly, if I were to take x equal to 4, I'd have 2 times 4 is 8 minus 6. So that's a positive numerator and a positive denominator. And the quotient of two positives is again positive. So this is the sign chart that we were talking about here. So we picked test points to create the regions, and then we evaluated those test points to note the sign of the result. So I've now done all but the final step of this process. The final step of this process is to go ahead and answer the original question, which was way back here. We want to know, where is this expression less than or equal to 0? So folks, careful, this is the hardest part. It requires a few examples to fully understand what's going on here. But I want to know, where is this expression negative or 0? Well, look, my sign chart tells me wherever this fraction would come out to be negative. So for my answer, we'll go from minus infinity to 0, and we'll go again from 2 to 3. Okay. And let me put a union symbol there, and I've deliberately left part of this out here, 2 to 3. So you'll notice what I haven't yet put on my answer are the endpoints. Okay? Because this matters. This is different from problem to problem. Certainly whenever one of my endpoints of the interval is kind of labeled as in minus infinity or infinity, certainly that gets a parenthesis. But what about these other three endpoints? Do I put a parenthesis or a bracket in each of these locations? This is where this sign chart is particularly useful. If you look up here, you can see that I've labeled that the expression is undefined at 0. So regardless of what inequality we're trying to solve, this expression does not exist if x is equal to 0. So I have to put a parenthesis there. Similarly, why was 2 labeled on my number line? Because the expression was undefined there. So I'd have to put a parentheses there because there's no way x could ever take on the value of 2. Okay, so wait for the other shoe to drop. Here it is. The third endpoint that I have to label is this endpoint at 3. But why is 3 on this number line? 3 is on this number line because it was a 0 of the rational expression. And look at our particular inequality. Our particular inequality says we want to know when is this expression less than or equal to 0. And so we do want to include the 0 value in our answer. And so this is our solution to the problem. Folks, if you thought this part right here is a little bit tricky, we're going to do some more of that next time. All right, I'll see you either in the next video or in class.